The standard normal distribution is a specific normal distribution. Anytime we see the word standard in there, we are referring to a specific normal distribution, which we can write as N01, which has mean 0 and standard deviation 1. The nice thing about having a standard normal distribution is that then we have one distribution we can use for everything instead of having to always generate different distributions for different means and standard deviations. So what we do to make anything work in the standard normal distribution is we calculate what's called a z-statistic, which converts from whatever normal distribution we might have to the standard normal distribution. And it does this by subtracting off the center. Remember that our distribution is centered at the null parameter. So we subtract off the center of our distribution. And we divide by the spread. So when we divide by this standard error, which is the spread of our distribution, we scale it so that it has also a standardized spread. So we're going to see how this works by finding the z-statistic associated with the sample statistic p hat equals 0.583 in the soccer home wins distribution, which was n 0.5, 0.045, where that 0.5 was our null parameter. And that 0.045 was our standard error. This standard error just came from a randomization distribution in this case. So my z-statistic is the sample statistic, 0.583, minus the null parameter, 0.5, divided by the standard error, 0.045. We would bring in a calculator for this computation. 0.583 minus 0.5, I'll evaluate the numerator before dividing, so that I get 1.84 repeating. 1.84 is plenty of decimal places for this. And this is actually a z-score like we saw earlier in this course when talking about descriptive statistics for one quantitative variable. What this means is that p hat equals 0.583, which is our sample statistic, is 1.84 standard deviations right of the mean, which in this context means 1.84 standard errors to the right of the null parameter. We know that it's to the right because it's a positive value. When we're sitting to the left of the null parameter, we will end up getting a negative z-statistic. Knowing how many standard errors we are away from the null parameter and in what direction allows us to place it on a standard normal curve. So here we have a standard normal curve. Note that this is centered at 0, so it clearly has mean 0, and we can kind of see that it has standard deviation equal to 1 by the fact that 2 looks like it is right about at the cutoff for the center, 95%, right? If we go out 2 standard deviations from the mean, we should get the center 95%. So we can verify that this looks like a standard normal curve based on that. I'm just going to mark that z-score of 1.84 on here. It would be between 1 and 2, definitely closer to 2, so that z-statistic I'll place right here and try to trace up to the curve and then fill in that tail area. So this is tail area from a standard normal curve. And if we compare it to the curve that we looked at that wasn't using the standard normal distribution, but instead was using the normal distribution centered at the null parameter and with standard deviation equal to the standard error, and we had, instead of our z statistic here, we had p hat marking the edge of this tail, they look otherwise exactly the same. So the curve using n0, 1 with a z statistic is equivalent to the curve using n of null parameter, which is 0.5, standard error, which is 0.045, and not using the z statistic down here, but using our sample statistic. So this first one here is really the method that's going to generalize well to everything we do. So even though this other one was helpful for getting us to understand what we're doing, we're going to leave this mostly behind and go forward with this process using the standard normal distribution. This will generalize much better when we start getting into other distributions as well. We always standardize first and then just work with one distribution. So with that in mind, let's go ahead and see how to do this in StatKey. On the home page, beside theoretical distributions, we are going to select normal. So here on the home page, theoretical distributions, normal, this is where I'm going to go. This automatically brings up the standard normal distribution. Even though it is possible to edit the parameters and change the mean and standard deviation, it's a good idea not to, so that we just do everything the same way. We'll stick with the standard normal distribution. I'm going to select right tail, which automatically brings up the right 2.5%. So we have selected right tail, and we see that z equals 1.96 for a tail area of 0.025 is what appears automatically. We're going to click on that box containing the 1.96 and overwrite it with our z statistic. Our z statistic, the one we just calculated, was 1.84. So we're going to change the 1.96 to a 1.84. And then we can see a graph that has the same p-value that we calculated earlier using the other mean and standard deviation, but it's now showing up in the standard normal distribution. So this number here up above the curve is the area of that tail, and it's equal to 0.033. Now this tutorial only covered a right tail, but certainly the way the mechanics work is the same as the way they worked for randomization distributions for anything else. I can select two tail and come and overwrite. Actually, I should reset this plot in order to illustrate that. If I select two tail and then overwrite this with a 1.84, then I can see that it automatically reflects my 1.84 to the other side and gives me two tails. If I were to accidentally overwrite the negative z-score with a positive value, it would look really confusing, so we want to be careful about that. That's going to make two overlapping tails and fill in the whole graph, right? So we want to make sure that we always overwrite positive z-statistics with positive numbers or negative z-statistics with negative numbers. Or similarly, we can do left tail and then fill this in as a negative, whatever value we want to try out, negative 2.5, and see what the area is under the curve if we are 2.5 standard errors below our null parameter.